All right, let's check out a few polynomial functions I have here. I labeled this part 1 because I want to do several examples, and these are just 2 to begin with. So also in the upper right, I wrote a few things to keep in mind. This is mostly what we're looking at, but as we go, might be a couple small things thrown here and there. All right, so first off, end behavior. And let me get one more color in here, kind of a lighter one. There we go. All right, the end behavior, what we're referring to is looking at that leading term, right? So we have an x to the fourth. Make sure it's in descending order. If not, look at the degree of the polynomial, and that's how you're going to determine end behavior. And the idea of that is because the larger the exponent, right, in a polynomial, this has the most effect when our values get extremely large or extremely small. So when I say extremely small, I mean a like tending towards a negative infinity, and extremely large tending towards infinity. So to think about that, if I did just plug in a small value like 10 to the fourth is significantly larger than 10 to the third, even multiplied by 4, and even more significantly larger than 10 squared. But that's just the power of 10, right? Like if I scaled this to 10 right here, okay, I mean, we'll see quite a change with the fourth power. But plug in something like 1,000 or 1,000,000, right? Like that, get an extremely large number in here, and we're talking billions and so forth. But even 1,000, we would really see the power of x tending to infinity. Because now 1,000 to the fourth, 1,000 times 1,000 times 1,000, right? Compared to 1,000 to the third, this is already 1,000 times larger. I know I have a multiplied by -4 there, but that really, it's irrelevant when we get to large numbers. Okay, so you may come into this video with prior knowledge of end behavior, and that's okay, but I did want to take a minute to describe that. So let me think about this. If I have, a very large number to the fourth power, it's going positive, right? It has a whole bunch of stuff that it may do in between here. We really don't know, like where it's going. But I do know as we move towards infinity, as x gets larger and larger, this function would shoot towards infinity. Now, if I substitute a negative value in there, because it's to the fourth power, it also is going to tend towards positive infinity on the y. Okay, so the end behavior for an x to the fourth that is positive, it would end high or begin high, right? It would decrease, and then at the end it would increase, and I don't know what it's doing in between. That's step 1. Zeros and the x-intercepts is something else we want to look at, and then test points, I'll explain that. The y-intercept is probably the easiest thing. I often start with the y-intercept because the y-intercept simply means to substitute 0 in for x, right? If x is 0, where does it hit the y-intercept? Both of these examples I chose, unfortunately, they have a 0, 0 intercept. That's okay. But if I substitute x as 0, right, I would get y as 0. And it may even help to have a little table of values here. I'm not going to go in any particular order. Like I might have some negatives and then positives. That's fine. Okay. So actually we're done with the y-intercept. So let's look at this x-intercepts. That means y has to be 0, right? And for a y-intercept, I let x be 0. For an x-intercept, I make y equal to 0. Well, that's going to require some algebra. To solve this now, always look for a greatest common factor. We can factor out x squared. Okay, and then set it equal to 0. So this factors to this. I'm sorry, set each factor equal to 0 now. And square root of 0, we get 0. X equals 3 and x equals 1. Really quick side note at the end here, I said a kind of a final check your intercepts, the terms, and the multiplicity. We'll talk about all those things. But this multiplicity shows up right here. Even though x equals 0 is only one solution, right? It's one intercept. The multiplicity is 2. What does that mean? Technically, I have x equals 0 and x equals 0 when I factor this. It's a power of 2, right? So the multiplicity is 2. A polynomial x to the fourth here, a fourth degree polynomial, has 4 solutions. Some of them might repeat though. Think of like x to the fourth equals 0. That has 4 solutions, but all 4 solutions are 0. Okay, so the multiplicity here, I'm just going to put an m, is 2. And that's important because an even multiplicity tells me that as the graph goes, because this is the first 0, I know that as the graph goes, it's going to hit this 0 and bounce up. All right, it will be tangent to the x-axis. It won't actually cross. Where the next few points at 1 and at 3, okay, this graph does some stuff, and then it crosses through 1 because this has a multiplicity of 1, which is odd, right? It's an odd number. This multiplicity was even. This multiplicity is also odd. It's 1, which means it will come up to 3. It will cross the x-axis at 3. All right. I think even though that is a final check, that is a great check as we go as well. Alrighty. So we have our x-intercepts. In fact, there were 3 of them. We had 0, 0, which we knew. We have 1, 0, and we have 3, 0. And actually, I want to leave just a little bit more room here. Okay. The reason I'm leaving a little bit of room, these test points for step 3 has to do with testing values in between the x-intercepts, right? So any value. And how this comes into play is if I know this is an x-intercept and this is an x-intercept, and I test what value do I get it to, I will get a negative in this one, but if it is negative, then all these other values, right, 1.5, 1.1, any value in between 1 and 3 should also be negative. So it doesn't matter which value you test in there. You test one of them to make sure your graph is sketched correctly. So I'm going to test 2. So we need to plug in 2 to the 4th. All right. Should have left myself a little bit more room, but I'm doing 2 to the 4th minus 4 times 2 to the 3rd plus 3 times 2 squared. Okay, and we could use a calculator, and in fact, we could pull up a table of values in our calculator, and I'll show that towards the end. But really quick, let's see what we get. We get 16 minus 32. 4 times 8 is 32, plus 4 times 3 is 12. So we get a negative 4. Okay. Now, we're doing a very rough sketch here. So I don't know exactly what this graph does, but right, like it might go a little bit lower and then bounce up. That's not what we're focused on. We're focused on the key things here. The x-intercepts, we have a couple test points to make sure, and then the end behaviors, and kind of check everything from there. All right. So because I said I will show you how to do a table of values, we'll actually use GeoGebra. I'm not going to get this exact value for a half. I'll just for now say that I know it's going to be positive because I pre-checked this. Okay, so I don't know where it's at. Maybe it's down here, maybe it's up here, but it is positive. All right, and then we should also check a value to the right here like 4, and we should probably check something back here like -1. And I know both of those will come out to be positive as well, and again we'll verify that. Okay, but we have somewhat of a rough sketch that's going on here. All right. So to check the intercepts, this number 6, I had said x to the 4th could have at most 4 solutions, 4 real zeros. We have 3. So we are good here. Okay, we're good on the intercepts, and I found the y-intercept, we're good. The turns. Because it's a 4th power, the most it could have is 3 turns. Now what does that mean? That means decreasing to increasing would be a turn. Increasing to decreasing would be a turn. So this graph is heading down and then it heads up. There's 1 turn. All right, then it increases to decrease. There's another turn right there, right? Second turn. And then it decreases to increase. Here's our 3rd turn right here. All right, so we are good with turns, and then we had already talked about multiplicity. So this graph, I mean, it looks reasonable. Okay, not 100% accurate, but it looks reasonable. Let's move on to the next one, and then we'll pull up a final check and kind of see, get a few more values and make sure that looks good. All right, and x to the 5th. This is odd, right? The degree is odd, and odd polynomial functions means that either we'll start low, do some stuff in the middle, and end high. So it increases and then does some stuff and it increases more, or it decreases, does some stuff and decreases. The easy way to remember this is just check a very large number, like, right, we're shooting x towards infinity, but we could even just do 10 in here. It would be positive, it's going to end high. And if you do a -10 to the 5th, right, that's negative, so it's going to start low, end high, do some stuff in the middle. All right, that's end behavior. Our y-intercept, like I said in the other one, I know it's 0 because if I substitute 0 in for x, I get y is 0. We'll start a little t-chart. So we plug 0 in for x, we got 0 for y. Let's check the x-intercepts. So 0 equals x to the 5th minus 5x to the 3rd plus 4x. Again, there's a GCF of x, factor that out. Okay, and the inner polynomial should factor, I believe, x squared minus 4, x squared minus 1. Yes, that looks good. Okay, we could factor again, or you could set each factor equal to 0. I'm going to go in a factor. I like difference of squares here. All right. So why I did it that way, when a lot of students, when they set x squared minus 4 equal to 0, they'll add 4 and then square root and just say x is 2. Okay, but remember, when you take a square root, you need the positive and the negative square root. So this should be plus or minus 2, and if I factor using difference of squares, right, it verifies that. I get x equals 0, this yields x equals -2, this yields x equals +2, -1, and 1. I have 5 zeros here. 1, 2, -1, -2, and the 0 as we had suggested. 0, 0. All right. So now if it, sometimes it would be better to go in order to see it, but it doesn't truly matter, and oftentimes we'll just want a table regardless. But let me go ahead and do this in somewhat of an order. Okay, so I have -2. I'm going to leave a little bit of room between each one. Okay, and the reason is, for our test points, we really want to try something back here like -3. I want to see what value I'd get when x is -3. And then in between -1 and -2, because I'd use a calculator, -1.5, right? And then -0.5. It doesn't have to be exactly in the middle, though. You could do -1.9. You could do -1.1. Okay, any value in there. 0.5, 1.5, and then I'm out of room, but something like 3. Okay, all of those I need to test to see exactly what's going on. I can also see, though, each of these has a multiplicity of 1, right? All multiplicity of 1, which means every time this graph will cross the x-axis. It will never be tangent. It will never touch like the first one. Now, I don't really want to plug all these in by hand, right? Especially these decimals, even if I wrote them as a fraction. I'd rather use calculator. So I'm going to tell you that when I do substitute -3, I'm going to get a negative something. Okay, it's going to be down here somewhere. Then the graph will cross through -2, and then I'll get a positive, right? Each of those in green were 0. Okay, I'm going to get some sort of positive value, and then it's going to come down, cross through -1. I'll get a negative value, and then it'll cross, I'll get a positive, okay, and then it'll cross, I'll get a negative, and then it'll cross, and I'll get another positive. Okay. And again, we'll pull up this graph here in just a second. Let's kind of make sure we have a decent rough sketch, besides, of course, getting the actual values for all those. All right, so we did our zeros and the x-intercepts. It's good. We'd use a calculator for our test points. We may need a few additional points. It kind of depends on, the uncertainties in your graph. And then let's check it. We have 5 x-intercepts, 5 real zeros. It was a degree 5, so that's okay. We can have up to 5, okay, 5 or less. The turns, we can only have 4 turns, so let's check. We went from increasing to decreasing. Basically, each of these peaks would count as a turn, right? So there's a turn. And then decreasing to increasing, there's number 2. Increase to decrease, 3. And decrease to increase, 4 turns. Perfect. We could have up to 4. It's 1 less than the degree. And the multiplicity, we already kind of verified. Like I said, I usually do that once I have my zeros. They were all multiplicity 1. That looks great. All right, so there's our sketches. Let's go check out. I had pre-graphed these in GeoGebra to save a little bit of time. There's the first one. Okay. We had talked about how it touched at 0, it crossed at 1, and crossed at 3. That looks good. Let me pull up the other one really quick. All right, so you can see all those values, right? I did a very, very rough sketch. And -3 and +3 are off the chart here. Even if I zoom out, right, those values are quite large. But I think it's important to see what's going on in here. Let's pull up this one. Well, before I do that, if you click on this in GeoGebra, okay, we could verify some of these things that we had got. They all look good. So these extremum, we're not going to learn in this class, but those are a few points you could pick. Let's look at this table of values. We'll start at -3, end at +3. And the step is like, how often do you want it to count? If we counted by 1, it would show the values for -3, -2, -1, 0, 1, 2, 3. I want it to count by half because I needed some of those values in between there, right? So now this is a quick way to calculate all of those intermediate values I was testing, right? So for instance, a -1/2, we got negative about 1.4. All I'd wrote in my chart is that it was in fact negative, right? -1/2, I got a negative. Okay, bouncing back. Let's go back to the function itself. There's the special points is often helpful, but that's quite a bit of information, and sometimes it's slightly off, and I believe the first example will show that. This one looks good though. All the roots, right, all the zeros are exactly what we got. The intersect down at the bottom with the y-axis, 0, 0, that looks good. Okay, let me hide this one and let's go this other one. Again, the table of values, we could see some of those points in there. Oh, it's still showing some of this other stuff. I don't know if there's a quick way to not show anything, but anyways, I can hide all that. It still looks like some things are showing up. That's all right. Okay. Also, I could pull up the special points here. And here's what I wanted to show really quick. Oh, now they're coming out right. Well, if you look at L, on here, on the chart where I highlight it says 1, 0. But if you look at L on the left, it's 0.99998, 0. Right here. So sometimes there is a problem with it trying to get so precise that there is a slight rounding error. Anytime you see that 0.99999, it's probably safe to assume you could round. Okay. All right. Anyways, I hope, and the more you get on here, you could hide or show them. Say you're done with this one completely, you could delete it, so that's pretty awesome too. If you're using your graphing calculator, it's done much the same way. You'll have y1 and y2, and you could pull up many of these points as well. Okay, I hope that helps with a couple examples and graphing these polynomial functions, and this kind of the 6 major things we're looking for in these in graphing these functions.